Now this diagram is drawn for a different question, and we'll get to that question and a couple of other things soon, but we're going to start over here. The question is, we have an object 7,000 kilometers from the center of the Earth, this representing the Earth. This dotted circle is going to represent a circular orbit around the Earth in a later question, but and 7,000 kilometers from the center of the Earth relative to the scale of the Earth. This being 6,400 kilometers, 7,000 kilometers would only be about here. I'm going to exaggerate a little bit and say we're out here, and we release something, and it falls toward the center of the Earth, and it falls to some other position. How much kinetic energy is it going to gain? Okay, we can't use MGH to calculate gravitational potential energy because gravitational force is not constant anymore. It falls off as the square of our distance from the Earth. So the specific problem we want to look at is we have a 1,200 kilogram object at a distance we want to get the expression for the force on a 1,200 kilogram object at distance r from the center of the Earth. Okay, and how are we going to do that? Well, imagine you blow me up to 1,200 kilograms, because remember we have the information that my 75 kilograms at the surface of the Earth experiences a force of 750 newtons. Okay, so a 1,200 kilogram force at the surface of the Earth, or mass at the surface of the Earth, would experience what? Where do I have it here somewhere? Well, I didn't. Yeah, I did. Okay, from 75 kilograms up to 1,200 kilograms, our factor is 16. So we're going to have 16 times the force, 16 times that 750 newtons, if I'm at the surface. Okay, now the Earth isn't changing. We're not shrinking it down to 3 kilograms or anything. So that 1,200 kilogram object would have 16 times my 750 Newton weight acting on it by gravity. Now we want to increase the distance to r. Okay, what's that going to do? That's going to change the force by what factor? Well, it's going to be 6,400 over r quantity squared. Okay, so we go from 6,400 kilometers to say 7,000 kilometers, then our r is going to change by factor. Well, it's going to change by factor 7,000 over 6,400, but being an inverse square, then the force factor is going to be this. Okay, so how much force do we have? We have my 750 newtons times 16, the factor by which the 1,200 kilogram mass exceeds my mass. The Earth's mass being the same, the product of the two masses will increase by factor 16. And then the reciprocal r squared factor is going to turn out to be 6,400 kilometers over r quantity squared. And that comes out 4.8 times 10 to the 8th over r squared, kilometers squared newtons. Okay, we get kilometers squared here, we get newtons here. And all the other quantities have their appropriate units. Well, basically, let's not worry too much about these. Those are the units of our force. And of course, when we divide by r squared, the units of r squared will articulate with these distance squared units, and we just end up with plain old newtons. Okay, now if we want to change the altitude from 7,000 kilometers to, there's a negative on this force also. Okay, let's talk about that. We got the Earth, we got the position out here. Okay, so if our position, if r increases as we go from here to here, then our force is going to be back this way, the force on this 1,200 kilogram object. So if r is positive in this direction, then our force has to be in the direction opposite r, has to be negative. So now we want to figure out how much energy it takes, or how much work is done by gravity on that 1,200 kilograms as it moves from the 7,000 kilometer distance to the 6,500 kilometer distance. So we're going to integrate the force function, this function right here, and it's a little crowded here, but there it is, the 4.8 times 10 to the 8th times 1 over r squared dr, and I suppressed the units, but the units are kilometers squared newtons, integrated from here to here. So we end up with this evaluated at 7,000 kilometers and at 6,500 kilometers. The integral of 1 over r squared, antiderivative of 1 over r squared is negative 1 over r. So we end up with negative 4.8 times 10 to the 8th times negative 1 over r evaluated between these limits. And I've got it written a little more clearly up here, including the units. The 4.8 times 10 to the 8th is Newton kilometers squared. And we multiply that then by negative 1 over r, which would be the 1 over 6,500 kilometers minus 1 over 7,000 kilometers. Now I've got a sign issue here that I'm going to stop and ponder for a second. Okay, sorry, it's been 24 hours since I did this. I should have looked a little more closely. I had a sign issue, but I don't. I have a negative here and a negative here, which ends up as a positive here. And then I can simply subtract the lower limit from the upper limit, the 1 over 7,000 kilometers from the 1 over 6,500 kilometers. Okay, and what do I get? Well, multiply all this out, do all the arithmetic. I think we end up something pretty close to 1.1 times 10 to the 5th Newton kilometers, which is 1.1 times 10 to the 8th joules. And I think there's a problem with that because I didn't correct something over here. So give me a second. And I'll work this through on screen. Square of 6,400 is about 40 million, 4 times 10 to the 7th. This multiplies out to something over 10,000, so there's a 10 to the 4th times a 10 to the 7th is going to give us a 10 to the 11th, not a 10 to the 8th. So we need a 10 to the 11th here and here. And then we need a 10 to the 11th up here. And then this, rather than being 10 to the 5th, okay, I have a couple of mistakes here. I estimated this pretty correctly as about 1.1 times 10 to the negative 5th. But then I didn't multiply that by my 4.8 times 10 to the 8th or whatever. This should then be something like 4.4 instead of 1.1. This is about 1.1 times 10 to the negative 5th reciprocal kilometers. And 10 to the negative 5th times 10 to the negative 11th is 10 to the 6th. So now we end up with 4.4 times 10 to the 9th joules. We end up with 4.4 times 10 to the 6th Newton kilometers, kilometer being 1,000 meters and a joule being a Newton meter. We need another factor of 1,000 to get to this. I recognized in class that my number here was low. I think that's pretty plausible. I think a single kilogram making that change is going to give you energy changes on the order of 1 million joules. So 1,000 of them would be in the order of 1 billion joules. So I think we're in better shape with this answer than the last one I had. And apologize for the confusion. Don't like to work these things out before class because people need to see the process, but it would be nice if I could work it out accurately in class, and I'm going to kind of try to pay a little more attention. Been trying to do that for a couple of weeks. Anyhow, with apologies, there it is. And you see that what we've done is we've used just the information, again, about my 75 kilograms, 750 Newton gravitational attraction with the Earth, and the proportionalities involved in gravitation, yielding this result. And this is should be fairly close to the accurate result that we could get. Now, we're going to go on and give the law of universal gravitation, just a quick preview, and then I'm going to cut, and then we'll come back to this. The force of gravitational attraction between mass m1 and m2 at distance r is, well, it's a proportionality. The force is proportional to m1, m2 over r squared. But we have to multiply that product and quotient by some constant which we call big G, the gravitational constant. Based on our 750 newtons between a 6 times 10 to the 24th kilogram mass and a 75 kilogram mass at a separation of 6,400 kilometers, we can evaluate G. We have everything here except G, and we determine that G is about, turns out to be 7 times 10 to the negative 11th Newton meter squared per kilogram squared. Now, of course, we're going to have to be careful about that kilometer squared. We're going to have to change that to meters before we square it. All the other units are going to be okay. And these are the units we'll end up with. Newtons times distance squared, meters squared after we make that change, over kilograms squared. And the actual measurement tells us that G is actually 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. The way we do those measurements is basically with lead balls in the lab. We can evaluate the gravitational constant by very accurately measuring forces on this scale. And we don't, well, we kind of measure them more or less directly, but we use a torsion balance and a lot of stuff that I'm not going to talk about right now to get this accurate result. Now, having gotten this accurate result, that's actually how we determine the mass of the Earth. We aren't given the mass of the Earth, the 6 times 10 to the 24th kilograms, so the information we started with is not the kind of information you would actually have from your more direct experimental results, at least not the mass of the Earth. You really have to evaluate this constant before you can figure out the mass of the Earth. We'll see how that works. It's not any more difficult than anything we've done.